Okay.
Okay. And there is recording of your and there is recording. We still have 2 minutes. So I should turn on the lights. Alexa will try to join
Okay.
the YouTube stream.
Uh-huh. Wonderful.
That's Christoffel Darboux. Oh, yeah, yeah. What happened? The lights? I thought we set out yesterday that these will be on. Otherwise people can't see. But maybe you just move the or not. Neither. Okay, so I think we can start. So it's a pleasure to have Professor Mihai Putinar from the University of California, Santa Barbara, and Newcastle University. He will be here for the next 3 weeks, and he will, as you know, give a series of lectures. Today is the first one, the Christoffel Darboux Kernel.
Thank you very much, Apurva, for the invitation, making it possible. I try to arrange my lectures, these seminars, in a string connected to each other. Today is the first one. And we'll touch a very classical subject of approximation theory, and goes back to Elvin, Bruno, Christoffel, and Jean-Gaston Darboux. These names are known to you for many important contributions to mathematics. For instance, Christoffel in differential geometry, or conformal mapping, Darboux for the geometry of surfaces, also for applications to analysis. He has an integral and so on. What I'm talking about has to do with orthogonality. And now we have the advantage of 150 years of accumulated knowledge, and we know what a Hilbert space is and so on, so we can see a little differently, but we cannot diminish their ingenuity and deep insight. So what it is about? We start with positive Borel measure, on the line, rapidly decreasing so that all polynomials are integrable. And I'll assume that is not a finite collection of point masses. That means that in the Lebesgue space, we can embed all polynomials of degree less or equal than n. Because we don't have only finitely point masses, this separates the points, and we have this embedding for every. And the whole story starts very humbly, very in a very simple way. We have for a polynomial of degree at most n, on one hand, the 2 norm, and on the other hand, if we fix a point in the complex plane, we have the point evaluation. Both are semi-norms. And the question is, how we compare one to the other? And obviously, this is possible. We are in a finite dimensional space with norms of linear functional semi-norms. And we can speak about the following quantity. We normalize this to be, for instance, 1 at lambda, and we take the minimum square norm. This quantity is achieved, and is the same as the minimum of the 2 norm divided by now the square. And this has a name. It's called the Christoffel function. Now, a good exercise for the linear algebra students is how we compute this minimum. And what is the significance of it? We'll arrive at this very early in this talk, when n is increasing. So the first observation, if we run with more polynomials, obviously the minimum decreases. So we have this simple observation.
So mu is fixed, you're going to vary that as well?
Mu is the measure.
That is the measure, it's fixed measure?
Is the measure which we fixed there. Obviously, this is true for every n. Therefore, the limit exists. It depends, of course, on lambda. This is the truncated Christoffel function. This is a full Christoffel function. And this is, of course, non-negative. Now, how do we compute this? If you are a little aware of the Hilbert space theory of inner space products, we immediately run into orthogonal polynomials here. Sorry. Namely, for every fixed n, we have a polynomial lower degree terms. We can normalize this so that the leading coefficient is positive, and so that the inner product in the Hilbert space is delta Kn. This is unique. It exists because the measure doesn't have finite support. And now, the second good exercise for the linear algebra students, how do we compute this minimum? We polarize. And we consider the following apparently artificial sum first. Sorry, K here. Usually, originally, this was defined for x, y real, but we can extend to the complex domain without difficulty, and the polynomial will have real coefficients and so on. Why this is relevant to our problem? Because if I take the orthogonality of the polynomials, this is a function of two variables.
On the right hand side, where is lambda?
Oh, sorry. My mistake. There is an n there. How do we find the point evaluation at some running x or lambda as you want? So we take our age and take the inner product with this quantity. If age is one of the orthogonal polynomials, this will be exactly the respective orthogonal polynomial. So this reproduces age, and is called a reproducing kernel in our modern terminology. Originally, it was Darboux who first thought about this function of two variables. And this gives us immediately the relation to our minimization problem, to our variational problem. Why? Because I'm looking at age of x is by the Cauchy-Schwarz inequality less than the 2 norm times the 2 norm of this sum. I'll write it in short. So our quantity, which is simply the inverse of this constant, is exactly the the function which was introduced by Christoffel. How do we compute this norm? Well, take the inner product with itself. And if we do this, we remark immediately from the reproducing property that this is the norm square. So what we have here is exactly the optimal constant. And as we know from Riess' lemma, this is attained, and we obtain immediately the formula for lambda. This was known around 1850 in a different language. And this quantity, the asymptotic expansion of this, we'll see immediately, is extremely important for a lot of problems of analysis. So I'm trying to show you a few of them. If you are familiar with the theory of orthogonal polynomials, I invite you to solve a very simple exercise, namely to prove the following Christoffel and Darboux formula. Let me see, K mu n xy. We introduce the leading term there. So this kind of Bezutian between the two functions will give us the reproducing kernel. Just use the orthogonality and be my guests and prove it. So first exercise. And in particular, if we pass to the limit with y to x, the Christoffel function inverse will be precisely Pnx Pn plus 1 prime x minus Pn prime Pn plus 1 x, something like this. This quantity is non-negative. Therefore, for every x, this is non-negative. Well, deduce from here that the zeros of Pn are simple, and the consecutive Pn plus 1 has interlaced zeros with Pn, and so on. So in this magic formula, which goes back really to the founders, the elementary theory of orthogonal polynomials is fully encoded. And is remarkable for two reasons: that we have a closed form, you write it on a postcard, and then you deduce all the interesting properties, as you know, of orthogonal polynomials, including the convergence we'll see in my second lecture of the associated continued fraction, and so on. So here it is, something really deep, and this was one of the first papers of Christoffel he published. He was very young in Berlin, student of Dirichlet, and this was one of his first contributions. Now, why this kernel is so interesting? Let's see an example. We can expand this, of course, to other supports. Here I started with a real line. We can go to higher dimensions. But first, let's remark something very simple. Suppose that the measure we started with has a point mass at a fixed point. Then I do the minimization at that point. Let's say this is real. But because this has a point mass, obviously this is bigger than the integral, and it will be the infimum in the end. The evaluation at age at x naught times the point mass over age of x naught. So for a point mass, the Christoffel function is strictly greater than 0. If we don't have a point mass, this is another exercise now for the analysis students. I claim that it will be 0. We cannot have point evaluations, bounded point evaluations, let's say in L2 of the 0, 1 with the Lebesgue measure. There are no point evaluations, so this infimum has to be 0. Otherwise, we'll have. So already this is a point. And now the exact statement is that in fact, here we have equality. Good problem for the Lebesgue space student. And it's much more than that. And now I'll simply state a remarkable series of inequalities which show the relevance of this quantity for the detection of point masses. So we turn the page. And I consider now a slight relaxation of the original problem. Namely, I say that two such measures are equivalent of order n by definition if they do not distinguish polynomials of degree at most n. Obviously, given a fixed n under measure, as you know, quadratures, there are many other measures with the same moments, with the same orthogonal polynomials up to degree n. And the following inequalities go back to Markov and Stiltius. Andrei Markov. And goes as follows. Mu is a measure as before. We consider a T so that the orthogonal polynomial associated to this measure of order n minus 1 is different than 0. And we consider the null points, the roots, of the reproducing kernel, which we have here. It turns out they are simple. This is a polynomial of degree d, so we have exactly n distinct real roots. And the first observation is that if we want to integrate h against the measure, polynomial of degree n, we'll have a Gauss-type quadrature. The coefficients are the following, and this is the interesting part. I can go, if I count the coefficients which are involved here, up to degree 2n minus 2. I have the weights and the quadrature nodes. So the integral is equal to this sum, a known fact to Gauss. But now what it is remarkable is that the coefficients are exactly the Christoffel function. And the original work of Christoffel was going exactly in this direction, to find the coefficient in this expression. And second, which is the contribution of Stiltius, is the following, that if we take the values of these weights, for alpha j greater or less or equal than t, this is bigger or equal than the distribution function of the measure on the closed interval, here we have the open interval, and is bounded from below by the contribution of the coefficients less than t. So in short, there is a difference here. If t becomes alpha j, we have a gap here, and the only term which is in addition is exactly that corresponding to the last one. Among all measures which are n equivalent to mu, the one which has maximal mass at the point, whatever t, is precisely the value of the Christoffel function. So it's a variational problem of a very intricate point, and this shows a lot. We will not go into this direction, but in approximation theory, this is quite remarkable. So this was done 25 years, 30 years after Christoffel and Darboux. Not our concern. Our concern is more modest. And to give you an indication, let's consider the simplest possible example. I turn now to several variables, real variables, and look at the unit torus in the complex plane. The invariant measure normalized has mass 1, and there is no decay at infinity. This is a compact support. We can very well speak about point evaluations of polynomials, but now complex. And if I do this, I run immediately into the orthogonal polynomials. Now, from your experience, which are the orthogonal polynomials? Just the monomials. E to the I theta, or if you want in the complex plane, Z to the N. It's an orthonormal system in L2 of the normalized measure. Everyone knows this. So let's take a point, lambda, in the complex plane, and see what is the Christoffel function. Let's denote this by mu. Well, I have to take the sum of the orthogonal polynomials up to the respective degree, and as you know, it's a geometric series, so it's lambda to the n plus 1, z bar to the n plus 1 over 1 minus lambda z bar. Sum of the orthogonal polynomials. The Christoffel function will be 1 over on the diagonal. So, very simple. Let's estimate this. On the diagonal. And first, on the support of the measure. Well, I have to pass to a limit, and it will be 1 plus 1 plus 1, n plus 1 times. You agree with me? Let's evaluate this outside. The disk. This will be lambda to the power 2n plus lambda to n minus 2 and so on plus 1. So if I do asymptotics, this is the leading term decides everything when lambda tends to infinity. So for sure, this has a geometric growth at infinity when n increases. If lambda is inside the disk, this is well known, is a polynomial, which is written there, but now the dominantic term is 1. And it will be, of course, the convergence is finite, and it gives us, in particular, finite point evaluations inside the disk for this measure. Yeah, so this converges for n to 1 over 1 minus lambda squared, and strictly positive. So very interesting. In this case, we get finite point evaluations, so points where the Christoffel function is positive outside the support of the measure. Now, why I mention this in detail? Remark the different asymptotics behavior. Here is going to infinity exponentially. Here is finite. And here is converging to infinity, but slower. Well, this is the starting point of a lot of interesting and recent applications. which have to do with this cloud of points and determining the cluster of them statistically and so on. I'll go into that. So now I'll turn to the slides, and possibly I'll give more insights as we advance. This is based on joint work with a lot of collaborators, but not yesterday. It's in the last dozen years or more. Not all of them are, in this terminology of today, pure mathematicians. Some are engineers, some are optimization people, but never mind, they all share the enthusiasm of Christoffel Darboux discovery. I'll go quickly over what we did. We have the orthogonal polynomials now. Let's work in the complex domain. The kernel, the so-called reproducing kernel. There are different terminologies here. The sum is up to n minus 1. Before, I used the sum up to n. So forgive me for this behavior. It's not essential. Christoffel, as I mentioned, and Darboux. Both of them were interested in approximation theory, in Gaussian quadrature, or really the asymptotic behavior of these developments for n big. The Christoffel function as we define it. And a little propaganda for my next talk. If you are interested in moment problems and you want to study this very delicate question of moment indeterminateness, namely, for what measures on the line the moments do not determine the measure, this is equivalent to the non-vanishing of the Christoffel function outside the real support for a single point. And if it is non-zero there, it is for all. So we'll see Monday this at work. As I mentioned, the maximal point masses. And I repeat, this is a very good exercise for Lebesgue theory if you want to practice a little your hand on sequences of functions. And the first probably notable contribution goes back to Szego much later, 50 years after Christoffel and Darboux. Why this is so important? First, he computed in finite terms exactly the Christoffel function. Now we don't take the rotation invariant measure. We take a weight, absolutely continuous with respect to arc length, and we compute the Christoffel function at the center of the disk. Believe it or not, it's exactly this geometric mean, which turns out to be magic for many interesting properties. Now, the geometric mean itself, that's rather easy to check, is also the solution of variational problem, precisely stated here. And this you can see rather easily because you can pull out a z to a power, and then you have the approximation of e to the minus it to z bar by the complex analytic monomials. So besides a byproduct of Szego computation, so I repeat, this was one of the first instances where the Szego, the Christoffel function was computed in finite terms, is the following remarkable theorem. We are 100 years after the founders. Kolmogorov and Crane. If you have a measure on the circle, it's a very legitimate question. Are the monomials, the complex monomials, dense in L2 or not? It turns out that this depends on the Lebesgue decomposition of the measure. So you have an absolute continuous part, you have a singular continuous part, you have a discrete part. And the system is dense in L2, in fact in all LP, if and only if this Szego condition is violated. That means the logarithm of the weight is not integrable.
Span of the monomials, right?
Yes?
Span of the monomials?
Span of the complex monomials.
System is dense, meaning the span is dense.
Oh, the system is dense. But there is a slight confusion. This W is the density, right?
That's the density, yes.
But why then do you need bounded variation for it? You have written W of t has bounded.
Well, the logarithm has positive, negative parts, and essentially, so W is non-negative. It's a density of a positive measure, and the logarithm can have positive, negative parts. And in fact, if you don't take the modulus there, you
Keep it with you.
you have minus infinity.
No, the theorem statement is okay. The condition that W should have bounded variation. Why do you need
There is no boundary value here. Everything is on the
Bounded variation. Right?
Bounded variation.
bounded variation.
that
Yeah,
necessary?
yes, of course.
Too high.
Why do you need?
Because the measure is a finite measure.
No, the measure is of boundary, not the density, right?
Yeah, the measure is a finite measure. It's a positive finite measure
So
on
you mean
minus.
to say mu has bounded variation?
Yes, of course.
W.
Yeah. The measure has finite value. Okay, so this is one of the first very interesting validations of this Gabor-Szego computation. Now, there is much more to do here. And I'll go into this direction. Essentially, what we are doing here, already we identified the point masses with the Christoffel function. With this theorem, more or less, and we'll see precisely, we identified the absolute continuous part of the measure. So we can do the analysis, the Lebesgue decomposition of the measure, strictly, and only looking at the Christoffel function. And this is something extremely interesting. If you look at the example we had here, of course the support is there. The absolute continuous part is detected by precisely this behavior. And now this is a theorem which we'll encounter a little later, but maybe it would be good to give you precisely the statement. So this was extended relatively recently. by the following theorem. We have a positive measure on the torus. And we assume that we have the Szego condition, namely that the integral of, I'll write like this. Of the absolute continuous part of the measure is integrable. Then, for almost everywhere on the torus, we have the following: the limit of n plus 1, or n doesn't matter, lambda mu n e to the I theta, is precisely the value of the absolute continuous part. So that's totally remarkable. This was proved in the 90s. And there are, by Wilmer-Stottik, I'll give references a little later, there are contributions more in this direction on an interval, on a collection of intervals, on all kinds of measures. The important thing is that we can recover the absolute continuous part just by manipulations of the Christoffel function. And this is really remarkable. Was discovered relatively recent. So we'll go in to see some applications soon. Lebesgue already knew the power of the Christoffel function, namely he was studying the convergence of Fourier type series. Now the development is with respect to orthogonal polynomials. And you see this simple observation. This is going back to Memoir and Annales de Toulouse of Henri Lebesgue. The maximum, so the partial sums of the Fourier expansion over all functions which are uniformly bounded is controlled by the Christoffel function. No surprise, because here we have, of course, the Cauchy-Schwarz inequality. But now the interesting part, if we want to study pointwise convergence of this Fourier expansion, not average, pointwise, we get immediately the approximation, the best approximation with a polynomial of the respective degree, which is the coefficient here, and the constant depends essentially only on the Christoffel function. So if you want to study pointwise convergence of Fourier type expansion in orthogonal polynomials for a given measure, regardless of what measure you choose, you get this. And now if you change the measure, usually the Chebyshev polynomials are better, sometimes Jacobi and so on. So these special functions will give you different constants, and they are all quite relevant for approximation techniques. I'll give you references to this. In the UniDisk, we discussed this, but now let's turn to the area measure in the disk, the so-called Berman space. There, the reproducing kernel, my colleagues here work on this, know very well, is precisely this. So the limit exists. And exactly as on the torus, if we study Inside, this remains on the diagonal bounded. Outside, short computation will give you an exponential growth if z is bigger than 1. And on the boundary, it will be of the order of n again. So it's consistent with what I said here. First application. We have a measure. Let's suppose that is the simplest possible. Just area measure in 2D against some shape, some region. And I want to approximate that region knowing only partial data. Now, tomographic data, radon transform, can easily be put into moment data. This goes back and forth. And of course, if we know this, we know the orthogonal polynomials. And the Christoffel function we just discussed is this quantity. We take the square root to be exactly the point evaluation. And the remarkable property of the Berman measure, the Berman kernel, is that if the boundary is smooth enough, the Christoffel function, this one, is comparable in a very precise sense to the distance to the boundary. Well, that's good news, because if I am outside the domain and I know the distance, I can recover the shape. Regardless that you are in a multiply connected domain, simply connected, doesn't matter. And on the boundary, this behaves, as we mentioned, like 1 over. K is the reproducing kernel is 1 over this, as you see. So we have a different behavior here outside on the boundary and inside. And from here, we can recover shapes. And here are some reconstruction experiments. I'll not give you all the details. We published this a long time ago. And it goes very close. It's very accurate. This is few moments, up to 10, 12 moments. And it recovers islands. We call them an archipelago. Our paper was called Analysis on Archipelago because we have many islands. And it's quite remarkable.
So your data is moments, is it? You are recovering from what is the data?
Tomographic data, radon transform. I can explain this.
No. I mean, here, this recovery is from, you said?
From the moments.
From the exact moments?
Yeah, from the exact. There is also an analysis of the error. So if you have some error, then you can analyze, and you have the error bounds and so on. So this goes more than what I mentioned here. Now, why this is remarkable? Because I mentioned moments. One simple remark. And maybe we take a short break. Yeah, let me make one remark and then we take a break. So computation of the Christoffel Darboux kernel. We have the measure mu. It's going in any number of variables. I'll mention it just for the real variables. How do we compute all this effectively? We take the moment matrix. Let's denote it somehow. These are the moments. We form the moment matrix, and as you know, this is a Hankel matrix, has equal anti-diagonals. If the matrix doesn't have point masses, this is strictly positive. The determinant is not 0. Then, the Christoffel kernel of order n is the inverse of this matrix applied to what we call the tautological vector, inner product with the tautological vector. So, matrix inversion, Hankel matrix inversion, there are fast algorithms, this is how we compute it. And the reproducing kernel, this is again a very simple exercise for the students, linear algebra, is precisely this. This, we call it like the Szego embedding, the Veronese embedding is the tautological vector, and this is the gate to compute effectively the Christoffel function and to do it and all. I'll give references to this. So maybe we take how long, Apurva? 10 minutes?
No, 15 minutes.
15 minutes break. Okay. So we can start. Thank you. Welcome back. We turn the page. The same Christoffel Darboux kernel, but now applied to a totally different field, namely dynamical systems. So we consider an ergodic dynamics with a transition operator T on some state space. And one of the basic ideas of von Neumann and then Koopman, his collaborator, I think student, was to transform the dynamics to look it from the perspective of observables. Namely, you take functions on the state space and you see how the dynamics influences by composition along the orbits, the functions. So this is the idea. You transform the dynamics in the ground space X into a transformation, composition with this T on a function space on X. And yes, there is something.
Yes, the receiver might be
Oh, sorry.
in the back pocket.
Much better, yeah?
Yes.
Okay. Sorry. So we use Koopman idea to put the dynamics on a space of observables. And if we have an ergodic dynamical system, means that there exists a measure on the state space which is invariant under this T. Therefore, the composition operator there will be unitary. Once you have a unitary operator, you know you have the spectral decomposition. Ries and Danforth and von Neumann spectral decomposition. The spectrum lives on the torus. You have a spectral measure which diagonalizes the operator. And if you localize this to an observable, this will be in the L2, will be a positive measure as we had before, supported on the torus. Well, the idea is that the Christoffel Darboux kernel, as we saw, can help us understand and uncover the behavior of the dynamical system, namely point masses of the spectral measure, the absolute continuous part, and the more delicate the singular continuous part are detectable by Koopman operator applied to the spectral measure of the operator. So we take such a generic vector function so that the span is the whole space. And obviously, this will determine U, is a bicyclic vector. And we have now the spectral analysis. What we are doing here is essentially spectral analysis of a unitary operator, namely the absolute continuous part, point masses, and the singular continuous part. As we saw, and this is rather elementary to prove, the pointwise limit of the Christoffel function, that means this inverse of the kernel, gives us the point masses. So already this is good news. We can see exactly where the point masses are located for the unitary operator. That theorem of Mate-Nevaeh-Totic tells us that if we do this weighted limit, now we don't take 1 over the Christoffel kernel, but 1 of the reproducing kernel, but n times it, this will detect almost everywhere the absolute continuous part of the measure. And something is left. Now, if we put this at work, we can distinguish between very nasty dynamical behaviors. And I'll show you only the tip of the numerical experiments, which were quite recent, and revealing for distinguishing from the Koopman point of view different dynamics. So here is a simple example. You take point masses, and you go up to 100 with the orthogonal, no, the degree, the trigonometric polynomials, and you see how they spike, and they tell you precisely where the point masses are. And on the other hand, you have here the absolute continuous part on this subinterval. So this is a toy example. If you go a little higher to 1,000, it is almost accurate. The absolute continuous part will be precisely this with dot reds. And you see that is quite close. And now it's indistinguishable from the experiment if you go to 1,000. Now, for a computer, this is not a big effort. You add a singular continuous part. You add the Cantor set measure. You know this very basic singular continuous measure. And the question is, what is going on here? Well, we have the same spikes. We have the point masses. The absolute continuous part is rather clear. But there is also some oscillation due to the Cantor set contribution. And you see that they are becoming quite relevant if you go again up to 1,000. Now, the question is how you detect that there is singular continuous spectrum. In general, you do spectral analysis of self-adjoint operators. Let's say Schrödinger operators, very important. How do you separate the point masses from the absolute continuous part and from the singular part of the measure, of the spectral measure? Very hard. There are some early contributions, and what we do here is remarkable because we use only the Christoffel function, and is quite accurate to give you the details about the support and the gap between different measures of parts of the measure of the spectrum. So, of course, you take the distribution function and you compare this with the distribution function of the absolute continuous part, and if there is a gap, and this is numerically detectable, then you win. And we put this at work. There is much more here. I'm telling you only about one experiment. There is much more going on right now. And you see the gap. So if you take the distribution function of the respective contributions to the measure, you see there is something missing, and that's an indication that there exists a singular continuous part in the spectrum. Quite clear in this experiment. And there is a singularity indicator. I'll give you references in the end. And this precisely detects pointwisely where there is the support of the singular continuous part. Now there are famous, so far was a toy example. Now we turn into standard dynamical systems on the torus. This is a so-called cat map, and quite recently was computed analytically, and our experiment shows precisely it matches the absolute continuous part. No singular continuous part, for instance, which originally is extremely hard to detect on the dynamical system. And the distribution functions of the respective parts do match. The famous Lorentz system, as you know, if you see it from different coordinates, it can be chaotic or can be very deterministic. And here you see that if you take different observables, so the different coordinates in the Lorentz system, you see immediately that for the third coordinate, there is a big gap between the absolute continuous part and the full measure. So there exists singular continuous spectrum. You can see for sure. And so on. I'll not go into much detail here because I want to show something similar. What is interesting, there are now in the Koopman operator theory, there are competing techniques. What I'm telling you here is only the Christoffel Darboux kernel, but there are other Fourier expansions and so on, resolvent growth techniques, and more or less they are at the same level of complexity and numerical accuracy. Flow in a cavity for the stream function, and again you have here a very big oscillation, and this shows obviously the presence of the singular continuous spectrum. So what I want to show you here, and I'll not go into much detail, these are computable, all the gaps and the numerical errors, is that you have, for instance, again, here in the cavity flow, you have a singular continuous spectrum. And then you can tell for sure that this dynamical system is not equivalent to one which doesn't have singular continuous behavior. And so I'll not go into much detail because we'll have something else to do. In the same direction, we have now, forget about the dynamical system, you have a big point distribution in two variables, can be in others. Can you detect the cloud from the outliers? Very big statistical question. And it turns out, what I mentioned before, you go into the ideal distribution, namely that the cloud is, let's say, absolute continuous part of the measure with respect to Lebesgue in 2D, and the outliers are point masses. Obviously, the Lebesgue distribution, the Lebesgue decomposition works like that, but what is remarkable is that the Christoffel function, even if you work with approximate data, will detect it. And there are many experiments here. You see the degrees are not big. The degree is 44 here, 20, and so on. And the outliers are very much isolated in the level sets of the Christoffel function. And there are, of course, many experiments. I show you only the little part of this. If you go up to 600, you can for sure detect the outliers and the gap between the cloud and the outliers. How you obtain just a little hint. Again, I'll not go into technicalities here. How do you obtain the error? Very important. Well, you study perturbation of the Christoffel Darboux kernel. This is a very classical subject, studied by approximation theory people for a very long time. And once you have this approximation in place, then you can see for sure that the level sets, the level lines of the Christoffel function will approach the support, but with a different rate, depending whether you have point masses or you have a cloud. And again, you have comparisons, some very simple observations in this, and it turns out that when you compare the ideal cloud with the approximated one, you have lower and upper bounds. You see with a very simple constants, assuming, and here this matrix comes full force, that you stay away from 0 and 1 in this Hankel matrix. So if you have good control of the spectrum of the Hankel matrix, then you can assure that the approximation of the cloud is very accurate. Therefore, turn into this. And so on. So there is a lot. I put all the slides here just to show you that there are very precise and probabilistic statistical studies on this. Again, I don't go into all the details. Very interesting associated kernel is the cosine kernel. So just for your information, if you do numerics with this reproducing kernel, the cosine kernel is as important as the reproducing kernel, this one. And I show you a little here what is going in one complex variable. Of course, we have potential theory there, the green function, and then you have super good estimates of the level sets of the decay or the growth of the kernel. You remember that, for instance, this quantity will go to the absolute continuous part of the measure. And a little toy experiment. Okay, we are in two variables. We can treat this as 2D real or 1D complex. Which is better? Complex, you will say. You are right. Always complex wins. Very good guess. And here is the example. Besides this, again, you can detect in higher variables whether the support of the measure is on an algebraic variety.
This is over complex.
Yeah. No, not necessarily complex. Now you can have real in this. Real. Yeah. So suppose that you have the data on hypersurface. How you detect it? Well, again, you go into the analysis of the Hankel kernel, and this will tell you precisely where you have the supports, and you detect algebraic supports with this. And there are many applications. I'll give you the reference in a minute. For instance, just for fun, how the dragonfly orients itself with respect to the sun. And there is this statistical data, and they show exactly the degree of the empirical Christoffel function. and so on. First reference, there is a book which we published last year. It's a tract in mathematics. Tract meaning that is a kind of guide. A long time ago, we had a LaTeX book which tells you only how to use LaTeX. So this kind of book doesn't have full proofs, but it's very instrumental to operate and has many examples of almost everything which I mentioned here and much more. How to play with the Christoffel Darboux kernel, and essentially to exploit the behavior of the kernel on the support, on the boundary, and outside. And this will give you more or less shape reconstruction, will give you Lebesgue measure decomposition and spectral analysis. So it's quite remarkable. So have a look. It's in Cambridge, and I think you know how to find a copy on the web. I don't mind. Last question, and maybe closest to the group in analysis at this campus. We saw the unit circle, and we saw that if you have complex polynomials, maybe I should repeat this because it's too basic and too important to forget. We have the Lebesgue space of the hard measure on the torus. And we take the closure of polynomials. Complex polynomials. A means analytic. They are not equal. This is the famous Hardy space. This is the full Lebesgue space. This is generated by positive, negative powers of the exponential. This is only positive power of the exponential, the Fourier modes. Basic question in general. You have a positive measure in the complex plane. Are the complex polynomials dense in L2? Are the rational functions with poles outside the support of mu dense or not? In this case, we know that they are not. Namely, the measure lives on the boundary, but every point inside is a bounded point evaluation. As we discussed. What is happening in general? Very big question which attracted a lot of attention in the 50s, 60s, 70s, and only relatively recently was solved, so almost in entirety, by Jim Thompson. He passed recently, was a professor at Virginia Tech. So let's read a little the statement, which is a little technical but relevant for what we are doing. We start with a positive Borel measure, now compactly supported in the complex plane. There exists a Borel partition, not closed sets, just Borel partition of the closed support of the measure, so that the closure of the complex polynomials is a direct sum of a Lebesgue space and closure of polynomials on these other parts of the spectrum. So the spectrum is complicated, has some spikes, has some holes. And this decomposition detects the continuum, the cloud, from the spikes and from the lower dimensional contributions. You have a complicated measure on this. Namely, you have the Lebesgue space where we know everything, but then the interesting part is that the other components each have a big cloud of bounded point evaluations, exactly as the disk has for the Haar measure. So each component has a, let's say, Hardy type behavior, except this one. Moreover, an element there extends as an analytic function inside the cloud. I call a cloud, this G sub J, is simply connected. And therefore, it determines the boundary. And if you look from the point of view of my colleagues here, the multiplication by the variable, this is a subnormal operator. The essential spectrum is only on the boundary, and so on. In particular, if this space is dense in L2, obviously these parts disappear completely. And we get, almost for free, the following, I would say, culmination of many decades of effort. Observation of Jim Thompson. The complex polynomials are not dense in L2 if and only if there are bounded point evaluations, if and only if the Christoffel function is non-zero at some point. This is for compact support. The proof was extremely hard. 91, published in Annals, almost nobody could read the details, was based on the decomposition with colors, with a lot of combinatorial topological consideration. There is a simplification now due to Jim Brennan, also a major contributor to this field. And the simplification is going to estimates for the connoisseurs here of Cauchy transforms of measure and bounds for the analytic capacity. Tolsa theorem gives some bounds on the analytic capacity of sets, and that will simplifies this. Moreover, what Brennan did, and I'll give you details, he extended this, not fully, but almost to a rational function approximation, again, if and only if you have bounded point evaluations. For the operator theories in this room, this has to do with the analysis of the subnormal operator, the Hermitian bundle anti-analytic of eigenvectors, of the adjoint, and so on. The density of polynomials we mentioned, and this gives us exactly, we go back with around the same result. If now we don't take the Haar measure on the circle, but an arbitrary measure, you have on one hand Kolmogorov-Crane result, and on the other hand the non-density of complex polynomials in L2. And is exactly related to the Szego condition. Now, with a colleague of yours, Shibananda, Calcutta, we tried our hand, what is going on in higher variables. And this is a very natural assumption to consider first algebraic affine curves. And ask, is Jim-Thompson theorem true on algebraic varieties? Now, if you have in higher dimensions, you don't expect point evaluations because the support can be on a curve. So it's very natural to restrict yourself. You take the Zariski closure to be just a curve. And we could do it only with standard manipulation, I would say, of push forward, pull back on rational curves. The idea of the proof is rather simple. I'll not go into much detail. You will see some examples very soon. But what is interesting, if you have rational curves, you need the approximation theory for rational functions, what was done by Jim Brannan. So even if you work with polynomials on the curve, you need you have the parametrization. There are some special points. You take them out, and of course, if you have polynomials here and pull back, you will get rational functions on the parameter space, and then you have to work with rational approximation. And magically, it works with standard techniques, with finiteness theorem and so on, and it gives us the result. But this opens a question, and here is my open question for everyone. What is happening for higher genus? Rational curves have genus 0. Is it true or not? And nobody knows. So that would be an extremely interesting point to start your hand. Of course, to understand the latest proofs of Jim Thompson and show that on higher genus, affine functions, regular functions, are dense in L2 if and only if you have bounded point evaluations. Now, you have to be careful with the topology, and I'll come to this in a second. In particular, this shows, again, for the operator theories here, that if you have a commuting subnormal tuple with a joint spectrum on a rational curve, always it admits invariant subspaces. So this is biproduct. Just for your fun. Obviously, this is rational. Yeah, you see the rational parametrization. Y is a rational function of x. It's a very simple curve. This is more interesting. And why I mentioned this trisectrix, because there are special points which are in the parameter space covered twice, or they are not accessible. And you can see the parametrization is not totally trivial. And how to prove the theorem, you have a measure on this curve, then you pull it back in the parameter t, you work there with rational function, you come back. So the general case, this is the open question, and I invite you to consider it. You work rather than on an affine curve on an open Riemann surface, and you have a positive measure there. You can throw away from the beginning point masses, and it's a technical assumption due to what we know so far that is not very wild. That means you have this open set which doesn't have finitely many components and non-reduced to a point. You have a measure supported there, and then the analytic functions, which are the analog of polynomials, are dense there. So the global functions, if and only if there are no bounded point evaluation. So that's a question of Christoffel function evaluation, and is open. In general, there are some observations here for hyperelliptic functions and so on. Let's take this very simple example. If I take the blue curve, the complement, let's say one point is at infinity, this is a hyperelliptic function. The complement is connected. So you don't expect bounded point evaluation, that would be everywhere. If you take the green curve, again. But if I take the red one, this disconnects. And for this one, the question is perfectly fine and open. Here are some references. I advise you, if you want to discuss a little and to enter into the details, this Brennan article is accessible. Jim Thompson, just for your curiosity, is not accessible, but is very beautiful. And uniform approximation was understood a very long time ago. And what I will not mention here, and this will connect with my fourth lecture, will be how we find the cloud of bounded point evaluations from the Christoffel function using operator theory. Namely, there is not a subnormal operator, a hyponormal operator. We'll do what I call the hyponormal quantization of the respective shape. And that will give us a very clear indication how to separate outliers from the cloud. What we did before with general Christoffel function, now we'll do it with operator theory, but only in my fourth lecture. Now, to finish, a lot of the classical theory of the Christoffel function is this in very beautiful survey of Paul Nevai. Let's count the number of pages. 164. He goes in a slow and details conversation with the reader into all details and the development of the idea of the Christoffel function from the point of view of approximation theory. It's a wonderful text which I recommend you. It's not really a bedtime story because you have to sit down with a pencil and understand, but it will pay back if you put the effort. So, but this is 86. And now of a more recent, and I'll finish with that, on a more recent contribution is Barry Simon, you know, big expert in spectral analysis and orthogonal polynomials. He wrote quite extensively on the Christoffel Darboux kernel. And he has new proofs and quite a lot of comments about, of course, the field of spectral analysis, qualitative analysis of Schrödinger operators, Jacobi matrices, and so on. And also is discussing something which I didn't touch in my lecture today, the importance of this object for random matrices and for the universality of the distribution of eigenvalues and so on. So this is also related to precise asymptotic estimates of the Christoffel function. And you can find them in Barry Simon article. So these are the two references, I would say, if you want to be a little more serious to follow up, have a look. And with this, I think I'll stop here.
Okay, get that because the mic is small one.
Okay. See Tirthankar Bhattacharya's page on Monday morning, the next lecture is there.